Yeah, so good morning. Let us start to this special asset colloquium special because it's on not Friday, and also unfortunately we also don't have the 4 p.m. slot available today, so it is going to be at 11 p.m. 11 a.m. Also, I'm sorry, the host of today's speaker, Shankar, has been in mute mode today. His throat is not well, so he delegated the responsibility to introduce formally today's speaker to me. I would have liked if he could actually say a few words about today's speaker. Okay, so the topic of today's colloquium is, can we define random close packing of spheres, what the speaker mentioned as RCP. Just a few words about the speaker. Doe is a professor in the Department of Physics at the Technion. Doe has made pioneering contributions to the theory of quasi-crystals, including the prediction of their diffraction pattern. In addition to his work on quasi-crystals, his research has been concentrated in soft condensed matter physics in general, particularly in granular materials, emulsions, and foams, and more recently on systems far from equilibrium on the quantification of unconventional order of solids. So with these few words now, I want to request Dov to start his colloquium.
Okay. So is this working?
Yes.
Okay. So sorry to get you here on a unconventional day and unconventional hour. And if you find the talk just terrible, just leave. I mean, that's what I would do anyway. It's a great pleasure to be here. I love to come to TIFR. I've been here lots of times at this point. And it's always an absolute pleasure. So thank you for inviting me, and thank you for coming to the talk. So what I want to discuss today is the notion of random close packing of identical spheres. This is a colloquium. I'm going to assume nobody knows anything. I'm going to assume there are biologists here, chemists here, in the lowest levels, string theorists. No, I'm teasing.
Mathematicians.
Pardon?
Mathematicians.
Yeah, you're right. They are lower than string theorists. That's true. Mathematicians are lower than string theorists. Apologize. Say so. I'm going to eventually insult everybody, and then everybody will be happy or unhappy. So I'm going to assume that nobody knows anything, and I'll give you the best of. I'll explain to you the best that I can about the ideas that we've been thinking about recently. And the work that was done in collaboration with Paul Chaikin, who's at New York University, NYU, Sam Wilkin, who is a student of Paul's, who's now at the University of California, Santa Barbara, Rodrigo Guerra, who was a postdoc of Paul's and is now working at the Impossible Meat Company, which is a plant-based meat company in the United States, which does pretty amazing things, and Ashley Guo, who is our current postdoc. So let me just start, maybe. Yeah, I knew this wasn't going to work. Now the problem is, this is the problem when computer people.
You have to click on the desktop.
Click on the desktop. Yeah, that would be good if I had a cursor, but the cursor doesn't. Is there a cursor? No. Life was so much simpler in the old days. All right. Excellent. So now I'm okay. So so let me start out by asking a question which has been of interest for quite a long time, and that is, what's the densest packing of identical spheres? I'm going to be speaking mainly in 3 dimensions, although I'll mention higher dimensions a little bit later, but not particularly much. We have some stuff to say about it, but it's a little bit preliminary, so I'll stick to what I know. So in 3 dimensions, if I pack spheres, what's the densest packing? So this problem was posed maybe before, but was posed for sure by Kepler in MDC XI, also known as 1611, in a gorgeous monograph called Die Neve Sexangula, which is on the 6-sided snowflake, and he was inspired by looking at the shapes of snowflakes, and this is now, mind you, this is now more than 400 years ago, and noting that they had hexagonal shapes, and they didn't know about atoms at that point. They didn't know about, I don't think, they didn't know about crystal structures and things like that. So this is an observation which would then be developed into crystallography, as a matter of fact, a couple hundred years later. In any case, so Kepler in this book, among other things, because he recognizes he's not able to answer the question of why snowflakes are hexagonal or have hexagonal symmetry, he asks all sorts of other questions along the way, one of which is about sphere packings. And so here's a picture. Let me see. So if this over here, you can see, I hope, that there's that he's building up spheres, and Kepler's conjecture was that the best packing that you can make is done as follows. You take a planar arrangement of spheres, or coins, it doesn't matter, okay, which was in a triangular lattice, just as I've shown right here, a hexagonal close packed arrangement of coins or spheres. And then what you do is I make several of these. I make a lot of these, okay, and I overlay them. So here, this is now overlaying the first, the second layer, and then he continues. And now there are 2 ways of doing that. There's this way, okay. Let me just do that again. The third layer is going to overlay the first layer exactly. In this case, okay, you can do that, or you can get rid of that top layer and a different third layer, which is now going to cover up the interstices that you can see through right now. Okay, that's the third layer. It's different from the first 2. It's not sitting on top of either one of those. And this gives rise to 2 different crystal structures. One is called hexagonal close packed. The other is called face-centered cubic. And both of them have a volume fraction, which is a fraction of space which is taken up by the spheres of pi over 3 root 2, which is around 0.74. Okay, and Kepler conjectured that this was the best you could do. And this is the sort of thing which now people say, well, every physicist knows. No, sorry, all mathematicians believe, and every physicist knows, right? That this was absolutely the truth, and it's important because if you want to pack things like cannonballs, you want to do it efficiently. Gauss, it would be really so nice if this thing didn't have that stupid "you are screen sharing" over it. But there's nothing to be done.
No, I think it is possible.
Can it be moved?
Yeah, yes.
You don't have a cursor there. That's the thing, because you're. I know.
Then there is a floating. You can hide that. I know, but you need to get cursor for it. Right. Cursor is not. Okay, you have to close it. Yeah.
But once any user.
Yeah, I know, but we will again, I'll do that. I'll do it from my phone.
But
Okay,
still
very good.
The pop-up will come.
Pop-up will it come?
Yes.
Yeah, of course, it's right.
Yeah, again. If any user comes, again. it will be pop-up.
I hate
Again,
Zoom.
it can pop-up.
Okay, let us do one thing. Let us move, can we move it down some? Move it down, as
Yeah,
much as down.
That's
straight
fine.
down,
That's
straight
okay.
down.
That's okay. That's okay.
Okay.
That's fine. And for now, it's fine. Thank you. Okay. So Gauss, about 200 years later, proved that those packings were in fact the densest lattice, what mathematicians call lattice packings, which physicists would call crystalline packings of spheres. Okay, but that's different from the more general question of whether it's the densest possible packing, including things which are not of lattice type. And you think about that, and the world of non-lattice packings is enormously large, and to prove that must be absolutely horrendous. And it waited about 200 years more, well, a little bit less, when Hales proved that this is in fact the best you can do, period, in 3 dimensions. And if I understood correctly, the Fields Medal this year went to I don't know her name, who proved that the same thing is true in 8 and 24 dimensions. If I if I get it wrong, the mathematicians won't yell, I hope, but will correct me later. Okay, so these are not simple problems. These are not simple things to prove. Okay, but this is not at all what you get if you dump a whole pile of balls, ball bearings, whatever, into a container. They don't settle into this perfectly lovely lattice structure, any of the ones that I showed you, or other possible layered structures. They don't do that. What they do is they go into sort of a packing which is, well, it's not crystalline. It doesn't sit on a lattice for sure. Its density is around 0.64. Again, density, I mean volume fraction, the fraction of space taken up by the spheres. It's about 0.64. And this is repeatable. I mean, you do this again and again and again and again and again and again. Different people do it, different countries, different size balls. It's always the same. It's always the same. Nature finds a way of finding this sort of structure, which has a volume fraction 0.64, roughly. Okay? And J.D. Bernal in 1960, who was studying glasses and amorphous materials, called this random close packing. And so the question is, can we define random close packing? That's what I'm going to address today. So it's easy to define a lattice packing, a crystal packing. It's easy. I just tell you what the crystal structure is, or what the symmetries are, and it's fine. I'm finished. Okay. But if I say I want to define something which is random, that is to say, is defined by the absence of order, can I really give a definition? Right? It's really something you have to think about very differently. Okay, and since there are infinitely many possibilities of ordered structures, it's pretty difficult to say it's not any one of these. I mean, it'd take you a long time. So the question is, can I define something properly by the absence of some sort of a quantity, which is in fact abstract order or something? What did it do?
Something comes up and I think you'll have difficulty. Only again that will to bring this.
Go ahead. Let me see.
Again, you have to break.
Why don't we kill Zoom? Then we could actually give a talk.
No, it's okay.
Should sit in the front row.
Pop-up आ जाता है sir.
I know, but you have to see.
Yes, thanks.
Okay. Okay. So the fact that it's difficult doesn't mean that people haven't tried. And Torquato, Truscott, and De Benedetti about 20 years ago suggested that you could define random close packing by looking at a bunch of order parameters, things which quantified order, and then finding the structures which would minimize those. And that's okay, except that, as I said, there are infinitely many of them, so it's not really a definition. I mean, it's interesting maybe to show that these structures do in fact minimize various ideas of order that we might have, but it's not a definition. Other people, Corey O'Hearn and the group with Sid Nagel and Andrea Liu, earlier on thought about these random close packings as being structures which arose so frequently because, as I said, almost no matter what you do, you'll get this sort of a structure. That means the basin of attraction of these structures must be very, very big, right? So think of it as a funnel, possible funnels. There are a bunch of exits into crystal structures. If your initial state is something, but the vast majority, they would say, funnels down into one of these random close pack states. That's a nice idea. It's not a definition, and if you do try to make it into a definition, then you'll have to confront the fact that there are very many protocols of constructing your packing, each one of which will modify the basins of attraction. So it's interesting to say, well, the reason that this occurs again and again and again and again is because the basin of attraction is large. It's almost certainly correct. Okay, but it doesn't serve as a definition. Practically, what people do, if they're not just pouring spheres into a large container, is that they generate random close packed configurations through computer simulation. And what you do is, the different ways of doing it, the best known is called the Lubachevsky-Stillinger algorithm. And what it does, it starts from a random configuration of point particles or tiny particles, doesn't really matter, tiny particles, let's say. I give them all some velocities, whatever. They're going to collide elastically, which means they'll conserve momentum and energy. Okay. And as these guys are bouncing off each other like a gas would, I'm going to swell the particles, okay, at some rate. Okay. So I have two time scales in the problem. I have a time scale coming from, let's say, the average velocity the particles have, and I have the swell rate, which is an artificial thing that I can control. Okay, so I'm going to swell these guys, and what you can see is that on the left, these are the tiny point-like particles, and I'm swelling them as I go, and I'll swell them until they jam, till they can't move anymore. Okay, infinite pressure if you care. But I'll swell them until they no longer can move anymore. And that's when I'm going to stop. Now, that's great, and it works very well. The control parameter, as I said, is the swell rate that I can control. And depending on the swelling rate that I use, I'll get different final densities. Yeah? Oh, physicists believe that in periodic boundary conditions. So, yeah, it's periodic boundary conditions. Okay. If I swell too quickly, then I jam at a lower density. If I swell too slowly, I jam at a higher density. And if you look at the structures that you get, you see crystalline regions, but that's not what you want. Right? You want this to be random. And so if you do it just right, exactly right, and stop it, right, at the right time, then you get an RCP structure. Okay? This is a great way of producing them, but it's hardly a definition. Yeah.
There's one, it is the amount of the crystallization of the boundaries?
There aren't any boundaries. It's periodic boundary conditions. Okay. Very good. Okay, so let me ask now what's known about random close-packed structures before I go into the modest proposal that we have. First of all, they're isostatic. What isostatic means is that they have the minimum number of contacts. Don't forget, these are hard spheres now. These aren't deformable. These are hard spheres. They have the minimum number of contacts to be rigid. So the whole structure is rigid. And so that what that means is that they have exactly the same number of constraints as degrees of freedom. And since I'm assuming that this is a random structure, I don't have worries about having constraints which are in fact linear combinations of others and things like that. So I'm going to ignore that possibility, which is of course what you would get in a crystal structure. And so the quick argument goes like this. It says each sphere in 3 dimensions has 3 degrees of freedom. It can move up, to the left, or towards you, let's say. Okay? So it's 3 degrees of freedom, each one. That means if I have n spheres, there are 3 n degrees of freedom. Okay. On the other hand, each sphere is constrained by the fact that it's in contact with a bunch of its friends. Okay? So if the J sphere has Zj contact points, then the total number of contact points in the system is n over 2 times the average of Zj, because each one is shared by 2. So it's n over 2 rather than n. Okay? And I equate those two things, and I find that in 3 dimensions, the average number of contacts equals 6. That's the minimum that you can. If you have fewer than that, the structure won't be rigid. At least somewhere won't be rigid. In D dimensions, this generalizes immediately to the average number. The average coordination number is twice the dimension, but that's I don't really need that for right now. Other thing that people look at is they look at what's called the pair correlation function, which is effectively the probability of finding a pair of particles at distance r apart. Okay, and when I look at 3-dimensional random close-packed structures, there are some characteristic things which you see in that in that pair correlation function, that 2-point correlation function. The first thing you see is that, so you have the first peak, which is just the contacting neighbors, right? Guys which are actually touching each other, and then you have the closest particles, close particles, which are not touching your sphere, a sphere in question. Okay, they're just a little bit further out, and that usually gives you a second maximum. In most cases, it gives you just a little second maximum. You have some local configurations which are more likely, gives you a second peak. In random close packing, that peak is split, and you can see it over here, right? This is the nearest neighbor peak, and this is the split second peak, and that's a characteristic. Yes.
In this algorithmic way of generating these, how robust are these statements to the rate at which you swell?
Oh, so this indeed would modify that, but I don't want to. I gave you the algorithm because I want to say that it's used to generate structures, but it's not definitional, right? It's not a definition if I say I have to tune this thing so that I get something that I want, right? That was the real. But yeah, the answer is it would definitely modify this. You'd see additional peaks if you have some crystalline regions. I don't know exactly what would happen. My guess would be that you'd see a rounding of the second split peak if I did it too quickly. Okay, the other thing is if you look at the decay around touching, okay, if you plot this on a log plot, you see that that's this thing over here, which is now the decay near the nearest neighbor peak what you see is it has a characteristic decay as a power law as a distance to the -1/2 it decays. Okay, or at least that's what we found some years ago. There's all sorts of questions about that, but it's the sort of thing which is reasonably well accepted. And so these are two things that we're going to have to compare with when I finally tell you how we want to generate these packings. We'll have to make sure that what we do matches up with these things, because if it doesn't, then we're doing something else and nobody will regard it as random close packing. Okay. So let me build up to the method by which I'm going to generate some packings by talking about an absorbing state model called random organization, which was invented by Paul Chaikin some years ago. And the easiest way to think about it is you take parameters in 2 dimensions. You can do it in whatever dimension you like, and you can use different shapes, but this is just fine. You take disks in 2 dimensions, spheres in 3 dimensions. You throw them down at random with some density. Again, I'll use periodic boundary conditions, so I know what density means. And if 2 spheres overlap, I'm going to give them a kick. Okay, a random kick, in random directions. So that would be something like this. So the guys which overlap are obvious, and I'm just going to give them a random kick. Okay, of drawn from some distribution with some maximum flat distribution with, let's say, maximum kick size epsilon in units of sphere radius or something like that. Okay. Only the overlapping particles are given a kick. The ones which are isolated are not. So this is a model which is sort of like the antagonistic neighbor model or something like that, where you just hate your neighbors and you want to move away, and that's what you're trying to do. Okay, and you continue until one of 2 things happens. Either they all separate and they're all isolated, dynamics ends, or the number or the fraction of overlapping particles, of active particles, reaches a constant. It fluctuates a little bit around the constant, but it reaches a constant. One of those two things will happen. This is called an absorbing state model. If the system finds a state in which there are no overlapping particles, the dynamics ends, it's an absorbing state. So this is known as an absorbing state model. These things have been studied a great deal in the physics literature. And this one that I just showed you is in what's called the conserved directed percolation universality class, which sounds wonderful to physicists and it sounds terrible to everybody else, also called the Mana class. And I'll tell you what that means. What that means is that the critical properties, and I have to tell you a little bit about critical properties, are the same for all of these different models, even though the models themselves look completely different. It's something which is well known to physicists in the context of equilibrium phase transitions. Okay, so this is similar, but we're not in equilibrium right now, and nonetheless you have universality classes, and this is the one. Okay, the Mana model is the following. I'm doing it again. You can do it in whatever dimension you like. This is easiest to draw. And what I'm going to do is I'm going to take a certain number of points and I'm going to distribute them randomly on the lattice. I have no problem with, in each plaquette, they can have as many as you like. I get tired of making more than 5. So I just threw something down. And this is an example of a configuration. I have to tell you 2 things about any absorbing state model. I have to tell you what active means. I told you a second ago that overlapping particles in the random organization model were active, right? And then I have to tell you what to do with it. I told you in the last slide that I'm going to give them a random displacement. Okay, I have to tell you the same thing about this model here. And this model, if the number of particles, if you like, in a plaquette, in a square, is greater than some number, and here I'll just take in 2, just you can take whatever you like, okay, is greater than some number, I will consider that the particles in that box active, and I'll move them at random to their neighbors, nearest neighbors. There are 4 nearest neighbors in this case. You can change the rules. You can move them to different places. That's fine. It won't change the critical properties. It won't change the universality class, but you can do it. Okay, so what I'm going to do is any place I have greater than 2 particles, I'm going to take everything out of that from that. I'm going to empty that box, and I'll redistribute the contents to neighboring boxes. Okay, so let's see. So you should. So if it's dying again.
Yes.
There must be a magic word. Okay, thank you. Okay, so look at all the sites which have more than 2. Okay, and I've moved everything around at random. There's still a few with 4 and 3. Those I will move now. There's one more site with 3. It's in the 4th column, 3rd row from the bottom. And I'm just gonna, because I'm tired of it, I'm gonna end this dynamics. Now, no plaquette has more than 2, and now my system is quiescent. Okay, dynamics has ended. I'm in an absorbing state. Okay. Now, had I put too many particles down, I would never find an absorbing state. I mean, it's obvious if I put on average more than 2, right? But even much less, I'll never find an absorbing state. If you like, I believe that it's more proper to say it will take me an exponentially long time in the system size to find it. That for any physicist is never, right? So if I exceed a certain density, a critical density, which I'll call rho C, then I'll never find an absorbing state, and dynamics will persist forever. Okay? And if you ask about the fraction of particles which are active, okay, as a function of density, if I'm beneath that critical density, ultimately I find an absorbing state. I have no more active particles. So that's shown in this. This is actually a phase diagram. That's shown. Are you going to do the same thing again? Oh, somebody wants to be admitted, but I'm not going to admit him. Yep, you got to do it again. Oh, it's okay with me. These guys don't need to eat lunch today. It's fine. So how did you do that? Just out of
just escape and this route.
Escape and that. Oh, okay, fine. I can do it next time myself. But the 8th or 9th time, I'll figure it out after being told. Okay, so if I'm beneath the critical density, I have the asymptotic number of active particles is 0. Asymptotic density of active particles is 0, and it rises with some characteristic exponent when I'm close to it. That's not the whole curve, but if I'm close to the critical value, just in the vicinity of the critical point, right around here, there's a characteristic behavior, which is that the active fraction behaves as the distance, and rho is greater than rho C here, from the critical density to some power. And that power is characteristic of the Mana class. Okay, it's true for any model which is in the Mana class, including the 2 I've shown you, and including many others which I haven't shown you. Okay. But the interesting thing, this is sort of interesting anyway, but the interesting thing is the fluctuations in particle number. If I look at a distribution that I get, either the Mana system or the random organization system that I showed you, what I can do is I can ask, as I choose a volume or an area, I choose a volume and I move it around and I ask what the fluctuations in the number of particles are. I can do that. So I want to measure the variance of the number of particles in a volume. If it's a random distribution, then I have the square root of n, the usual square root of n fluctuations, right? That you expect, and so the variance would go as the volume. Okay, in that case, and that's sort of the variance. This is the variance in the number of particles, and that's going to go as the number of particles in the region, which scales as the volume of the region because the density is defined, is well defined. If, on the other hand, and here I'm just being careful because there are mathematicians in the audience, I take a periodic lattice and I give slight kicks to the points at random, and I do the same trick, then what I find is that the variance in particle number, in fact, doesn't grow as L to the power dimension, okay, L being the characteristic size of the region you're looking at, but rather as L to the power d minus 1, because the fluctuations are coming from the periphery, from the boundary, okay? So it's the area or whatever dimension you are, that's what's giving you the, inside, doesn't matter that you've displaced stuff, it's perfect, it's fine. So the question is, what do I get for these nanosystems? Well, I wouldn't be bringing it up if it were trivial. What I want to write then is that I want to write the variance in particle number now as characteristic size to the d minus alpha. So alpha is 0. This was originally in slightly different order, which is why alpha equals 0 is on top. Alpha equals 0 is the random distribution, and alpha equals 1 is the let me call it the periodic, the crystalline distribution, if you like. And remarkably, the critical states of these monosystems are what are called hyperuniform. And hyperuniformity is a concept which was developed, was introduced by two groups, but I believe Gabrielli and his group, if I'm not mistaken, and Torquato and his group in completely different contexts. One cosmological and one condensed mattery, and they were describing systems whose fluctuations, and number fluctuations, let's say, are greater typically than greater typically than a crystal lattice, for example, but less than random, less than a Poisson process, let's say. So they somehow have reduced fluctuations, okay? And so that would be the case if you have alpha greater than 0. And I'll tell you the value of alpha in a second. The value of alpha in the monosystems depends on the dimension of that you're looking at. In 3 dimensions, it's 0.025. It's around a quarter. It's not exactly that, but it's around a quarter. And what that means is that the critical states of the monomodel have reduced fluctuations. And I want to just tell the physicists here why this is really shocking. This is shocking because you learned that at an equilibrium second order phase transition, at the critical point, fluctuations diverge. Okay? Fluctuations diverge. That's absolutely, and that's all you ever, that's all you were ever told. And it's true. In equilibrium, that's absolutely true, provided you have short range interactions. In this case, you have a critical point. I haven't gotten into all the details proving to you that it's a second order phase transition. It is, it smells like a second order phase transition. It takes like one, it must be one. And yet, instead of having diverging fluctuations in that critical state, you have vanishing fluctuations, not vanishing, but reduced fluctuations. This is something which can occur in equilibrium. This is something which very rarely, the only cases we know about it, in fact, are models like this. Okay, and this, I'll give credit to my student, Daniel Exner, in 2015. We discovered this. And so here's a picture of a critical state of that rand-org model that I showed you in 2 dimensions. And here, just to contrast it, is a random. It's not quite a Poisson process because we have these things being separated, but it's for a physicist, you'd say it's a Poisson process, but that's because we're very imprecise. Okay, but it's we just throw these things down, but we don't allow them to overlap. That's all. So just to go back, right? So whoops. So that's what these two things look like. Okay. The way this is typically discussed is what's called the structure factor, which is defined right here for you. It's the square of the Fourier transform as a function of wave vector, a function of k. And if you look at the small k behavior, which is a large wavelength behavior, large distance behavior, what you find is that this quantity here goes to zero, typically as a power law, if the system is hyperuniform. It's going to go to zero as k goes to zero as k to some power. It's the same alpha, in fact, that we saw a second ago. Okay, so it's going to be 0.025 if I remember correctly, and that's just fine. Okay, let me now change the rules a tiny bit, not that much, just a little bit, and I want to introduce a model called biased random organization. And the bias is because now we instead of just giving these guys a random kick when they overlap, we sort of want them to repel each other a bit more. Okay, so they, instead of going in random directions, they have a component which separates them along the lines of their centers, joining their centers. Okay, you can make it more or make it less. That's just fine. The repulsive displacement, as I've given over here, is going to be, well, it doesn't really matter. It's fine. I'll tell you in a little bit. The dynamics. So these guys now are separating. Want to separate more. There's some component of randomness which you can make small. It doesn't really make any difference as it happens. Okay, and this was some recent work which we just published fairly recently. It turns out that the critical behavior is the same as it was for the Mana systems. Okay, which is not obvious, but it turns out to be true. And I did get the alpha right. It's around a quarter. Okay. And the question now is, what do we find for the critical state? So I want to now bring this, eventually I'm going to bring it back to the original, to the way I introduced this, the whole thing. So first of all, let me look at the density. The density of these critical packings. So again, I take a bunch of spheres, throw them down at random, okay, at some density, at some volume fraction. Okay. No, excuse me. I don't. Yeah, I do. And I let these guys do their dynamics, moving apart with a bias towards separation, and I can change the size of the maximum kick size that I give it. I mean, if these things overlap, I can throw them like this. I don't want to do that. I want to make little tiny little shifts as it happens. So on the x-axis, there's the maximum kick size. So if I do something like this, it's on the right side. That's a really large epsilon. And if I do something like this, it's on the left. It's towards the left. And what I see is that, and and the amount of randomness is given different amounts of random kicks in addition to this repulsive one are given in the different colors. It doesn't really matter a whole hell of a lot. The only thing I want to point to, and you can really see it best only, I would say, in the two curves, because it gets very, very difficult to simulate because things take a long time, converge rather slowly. What I want to call your attention to is that the critical density, okay, in this model, first of all, it depends on the kick size. And as you make the kick size smaller and smaller, as the kick size goes to zero, you get a distribution in three dimensions, which has a volume fraction of 0.64, close to, okay? Which is the same density, same volume fraction as you have for random close packing, okay? So that's good. We're happy about that. We have a system which has which looks like it has a density of random close packing, but as I said, you have to compare it to other methods of generating packings to make the statement that this is random closed packing. So let's just do that. The pair correlation function does indeed have this Batman split second peak, okay, which is nice. Again, the different colors correspond to different kick sizes. If you make it very big, that second peak is no longer split. Okay, you're at some structure, but it's a different structure. If you look at the decay of that first peak, the one that I said decayed as the square root of the distance from the contact, it does indeed appear to do that. Okay, so we would say, and the last thing is, if you look at that structure factor, that thing which I said should go to 0 for a hyperuniform structure as the wave vector, as k or q in this case, I changed the variable, goes to 0. Okay, if you look at the figure here, there are three overlaid. They're the results from overlaid from three methods of producing random closed packing. Well, the one that we are purporting to produce random closed packing, and two which are acknowledged to produce random closed packing, and they overlay exactly. Okay, or I mean exactly as physicists would say anyway. Right? And the interesting thing here is that this goes to 0 with a slope. This is a log plot with a power of 0.25. Goes to 0 is q to the roughly 0.25. So what we're saying is that random closed packing in 3 dimensions is hyperuniform, and we're telling you what the hyperuniformity exponent is. Now, what's the point here? Okay, the point is, as I said, that for as long as I take my maximum displacement size to go to 0, I'm going to get a structure which looks like random closed packing, as well as anybody. I mean, we've done everything that anybody asked for, and there aren't any other things we can compare with, and so this is it. So we would say now that this method gives random closed packing, but why do I say it defines it? It defines it because we're talking now about a critical point of a statistical model. Okay? Statistical, and that is a well-defined, if I say there's a second order phase transition at some point, okay, that point is not negotiable, right? It's not like a glass transition where if I do things more slowly, I can do a little bit better. If I do things too quickly, it's worse, whatever the story is, right? You all know that at whatever atmospheric pressure we're talking about, water boils at 100 degrees, right? It's not negotiable, right? If you put up if you make the flame bigger or you make the flame smaller, it doesn't matter, right? It is precise. It's precise. Second order phase transitions, well, phase transitions in general, are precise objects. And therefore, this now serves as a definition of random closed packing. At least, I mean, somebody can come along and say, no, it's not because it doesn't do something else. Possibly, but then they'd have to figure out what the difference is and they have to show that theirs is better, right? I don't rule that out, but I don't see why that would be the case either. Okay, so this I would argue defines random closed packing. And let me just say one thing. I mean, these absorbing state models are sort of funny, right? Clearly I can start off in some initial state which won't go to at this critical density. I can put things in by hand which will screw up the critical density. Okay, but those are measure 0. Okay, with probability 1, you throw things down at random, it's going to do what I said. Okay, and the fact that you can do something really uber clever and arrange something in a certain way and say, it doesn't work. Yeah, okay, fine. Right? With probability 1, this is the behavior that you get in these models. Okay? Okay. The second point is, as I said, what we're saying is that random close packed structures are not really completely random, which is could have guessed because there are constraints like they can't interpenetrate, right? But we're saying that that these structures at the fluctuations, the number of fluctuations in these structures on large scales, in any case, is smaller than it would be if the things were random. This was absolutely not an obvious point. Torquato and his group also claim this, but they got an exponent which was not correct for uninteresting reasons. Okay, which I can tell you about, but it's not really that interesting. Okay, so this is really characterizing the structure. So let me conclude. There are lots of things I could go on speaking about, but lunchtime is eventually coming. Look at that! It's actually been an hour. So first of all, I want to claim that random close packing can be defined as the critical states of this bias random organization model, provided that you take the kick size to 0, small kick size, as a definition. This has implications. Among them are that random close packing are hyperuniform, reduced fluctuations. This gives information about the radial distribution function. These things are long-range correlated in the sense that physicists mean. The correlation function dies off as a power law. All this stuff, which is interesting to physicists and probably to nobody else, I'll just throw out for people who are primed to hear it. And you can ask what happens in higher dimensions, for example. In higher dimensions, it's sort of funny. So in higher dimensions, so we've looked at 4 dimensions and 5 dimensions. Okay, and what you see is that we get using this, we get the same hypervolume fractions, whatever you want to call it, the same densities as has been obtained by a couple of other groups. The density is monotonic decreasing as the dimension increases. Okay, the specific numbers aren't of that much interest. Just to say that things look good. However, in these monosystems have what physicists call an upper critical dimension, which is 4. And upper critical dimension means that above 4 dimensions, all the critical exponents are the same in all dimensions. Okay? And it's not hyperuniform. In that sense, well, let me make the statement in a second. Okay? But if I have in higher dimensions, the systems are not hyperuniform. Let me just stop there for just a second, and then just ask about 2 dimensions. There's a lot of interest. People are really quite interested in, can you get a random close packing of disks? Different people say different things. Typically, if you did the same experiment instead of ball bearings or whatever, throwing into a container, you did it with coins, you're going to get a triangular lattice. That's what you're never going to see anything else. You might have some grain boundaries, right? The orientations, but you'll have crystalline regions, no question. So you could add, it begs the question of whether you can actually have a structure which is random. I'll just say that we don't find one. So that's our contribution to that debate. So let me just imagine that in 2 dimensions you cannot have random close packing of identical disks. Let me just say that for a second, and I'll be attacked by the internet trolls, but they won't see this, so it's okay. And what that would be saying is that in 3 dimensions, random close packing is the most ordered in the sense of reduced smallest fluctuations of any dimension. Because if I say in 2 dimensions there isn't any, 1 dimension you know there isn't, right? And 2 dimensions, if I say there isn't, 4 dimensions and higher, it's not hyperuniform. Only 3 dimensions then is hyperuniform. That would, if you allow me to define order as being as being indicated by reduced fluctuations, 3 dimensions is the best you can do. So anyway, that's all I wanted to tell you. Thank you very much for your attention, and I'll be delighted to try to answer questions.
Thank you. Thank you. Very nice talk. Yeah. Sure.
How
Kedar.
do you make this identification with the RCP and
Sure.
And you said because of the upper critical dimension in 4, you don't get something in this beyond. But what's the lower critical?
Yeah, it's a funny thing. Yeah, I think it's 2. I mean, 1 dimension is sort of funny. If it splits up into 2, 1 dimension is a problem.
So then the statement that you won't see.
But I don't really know what lower critical dimension means in this particular system. So let me not answer that.
The question is, there is this identification to a critical point.
Is there a much simpler sort of lattice model one can write down, which will get some statistical properties of RCP right without going through the particular realization you're at?
Well, I mean, you'll if you use the mana model that I gave, you'll get the correct critical exponents.
Alpha.
You'll get alpha. You'll get you'll get the exponent describing the increase in the number of active particles, time scales, stuff like that. You can do that, but you won't get anything structural because it's a different model, of course. I would say.
Any other question? No.
Everybody's hungry.
No, I thought we are still.
Oh, okay. In that case, you have to ask questions.
Okay, so there are no more questions. Once again, let us thank our speaker for his wonderful talk, and also thanks Shankar for bringing this talk possible. Once again, thank you.
Hi, Dov. Can you hear me? I have a question actually regarding this. If you're there, can't hear it. Okay.